Okay, let me start. First of all, as you may have seen an announcement, I've extended the due date for assignment 6 by one class period. That is to say, instead of this coming Thursday, it's due the following Tuesday. The image data file the images had failed to be normalized, and now they are. And so when you finally compute with the image file, please realize that they were changed, and you should use the ones that are there now. The LAs tell me that they expect the MATLAB grader to be up for this exam by tomorrow afternoon. After this programming assignment, this is the last programming assignment on material that will be covered in the exam, the midterm exam. And we will be continuing on in lectures on new material that will be covered in later assignments and in the final exam. Of course, the final exam will cover the whole course. I will issue the next assignment, assignment 7, immediately upon the receipt of the midterm exam, and you'll have it for about 2 weeks. And then that one will be on the stuff we're doing now, these multi-scale approaches. And then we will have gone on to a topic called geometric transformations in 3D, and transformations such as rotation of an image in 3D or perspective projection from a 3D scene to a 2D image like you would have onto a camera, and so on. And there will be an assignment on that, and that will be the final assignment. There will be material covered after the material that the final assignment is on, but there's no time to have yet another assignment, so there won't be an assignment on that material, and yet it will be covered on the final exam, the material in that final section. Any questions about the plans for that? As for the midterm exam, a week from Thursday, which is the last lecture before spring break, I'm going to present a summary of the material so far. Well, a summary of the material up to the time that I said the exam material stopped. And the following week, the week of March 14th, the work week of March 14th is spring break. You'll come back and we'll have a lecture on the 22nd of March. I will cover the 2020 midterm and its answers and any other final questions that you have. You're welcome to ask questions related to the exam preparation during the time of this summary lecture and on this Tuesday. We'll pass out the midterm on Wednesday the 23rd, and during that time there won't be an opportunity for questions on substance. The only kind of questions will be administrative. If there's a question on an ambiguity or a typo or some problem on the exam, of course, those will be fielded, but not on, I don't understand some material, please explain it. It will be due on after that weekend, Okay, so you will have the last part of that week and the weekend to do this exam. The exam will be designed to be doable in 75 minutes, but my experience is you all take a good deal longer sometimes, and that's okay. On the very next lecture after the exam is due, I will publish the solutions and we'll cover them in class. So you get a chance to understand things that you might not have understood. Any questions on the plans? Yeah.
Would there be coding questions?
No. The exam that you saw an example of, is a real example. Those are the kinds of questions that will be asked. They will test your understanding of the material. Okay. Any questions on anything we've covered so far? Okay, so we're talking about a particular means of producing representations with locality, and that have a possibility of multiple scales. We'll get to the multiple scales shortly, but we're talking about the particular problem of splines. We're going to talk about splines in 1D first, because splines in n dimensions for n greater than 1 are produced separately, meaning you first do it in one dimension, and then the results in one dimension produce the control values for the next dimension. So you do it on the rows in X first, for example, and the results produce the control values for the application in Y. And if you are in 3 dimensions, then those results will produce the control values for the application in Z. So it's successively applied dimension by dimension. And so we're talking about any one of those dimensions. Here I'm calling it, say it's the X dimension. But it doesn't matter. I'm going to talk about a set of values that are indexed by a parameter t. And t is simply a counter of how many sample input values you have. They are equally spaced, right? So you have one at t equals 0, one at t equals 1, one at t equals 2, one at t equals 3, right? And we're going to be interested in getting values at t, at any old t. T equals 1.579 or t equals 8.346 or whatever, okay? So we're going to be evaluating this. And the whole idea of splines is that it's patchwise. That is to say, if you are in patch 1, which is to say between t equals 1 and t equals 2, so any t like 1.2 or 1.7 or 1.9 or whatever is in this patch, we're going to use a particular polynomial in that patch. And that particular polynomial is given here, and I'll say more about this and its relation to the expression up there on the screen. The ideal, okay, so the thing that makes a spline is that it's patchwise, and that it's polynomial in each patch. And strictly speaking, it's a different polynomial in each patch, but the polynomials fit together very nicely so that the polynomial that you use in patch one, the patch that goes from 1 to 2, which is shown here an example in black, fits nicely against the polynomial in patch 2 to 3 at this boundary between the patches, right? Which happens, in this case, at t equals 2. You switch from patch 1 to patch 2. And the idea is that the whole thing is arranged so that the values in this patch and the values in this patch agree. They're continuous in value. That is to say, right at t, if you evaluate the black patch at 2 or you evaluate the red patch at 2, you will get the same value. But not only do they agree in value, but depending on the particular spline that you use, there's lots of different possible splines. The one we're talking about is called the B-spline, okay? But there are many splines, and depending on the spline that you use, you have it satisfying certain continuity in derivative values as well. And so for the B-spline, it's arranged so that the first derivative, the slope of the spline, agrees across that patch change location, and that the second derivative is continuous as well, which is roughly something like the curvature of this curve. Got to be careful about the word curvature. It has a special meaning. It's a second derivative kind of thing. And depending on whether the derivative is with respect to t or with respect to distance along the curve, you get a different meaning of curvature. But in any case, the second derivative here is continuous. Okay? So, there are so-called interpolating splines. They're still patchwise, right? But the input to a spline is a control value at each of these integer places. At t equals 0, there's a control value. Here it's shown by this dot. At t equals 1, there's another control value. At t equals 2, there's yet another control value, and so on for all the way down. For every integer position, notice the equal spacing here of t. You have control values. And ideally, to make it have locality, you'd like the control values that are associated with a particular patch to be near that patch. That is to say, if you change some value out in patch 17, it does not affect the piece of the spline at t equals, that begins at t equals 2. Okay? But it turns out that if you really want the spline to match, to actually pass through these control values, a so-called interpolating spline, a so-called interpolating spline, you can't get this local support. You can't get just it depends on values nearby. It's global. That is to say, you change one value. If you want it to be interpolating, you change one value in the 17th, for the 17th control point, it's going to change the polynomial in the second one. And that's not really desirable. So normally, splines are not used as interpolating. Instead, they're approximating. That is to say, they pass near the control values, but not necessarily through them. They have the right kind of behavior in the sense that if I take this control value and I pull it up, then the curve will pull up. If I pull it down, then the curve will pull down. Okay, but not in a way that makes it actually pass through. So B-splines are approximating splines. And Okay, and so, you know, you can go, whoop. What's happened here? What is this? I'm not sure. Screen. Working fine. Stop share. Boy. I have a picture on my screen that I said to share, and I can't get it to share.
Is it Ford? They maybe a Ford fell out.
Yeah, maybe it did, but it doesn't hurt this. I'm going to reseed it. Yep. Most peculiar. You know, standard problem, you reboot. Anyway, okay, so this is just an example. The asterisks here are the control values, and the curve, the smooth curve, is the spline that passes near them, right? So if you want to evaluate the spline for any particular value of t, let's say for 2.64, then you know you're in the patch between 2 to 3, and you're going to use the patch that begins at t equals 2, the second patch. And you're going to evaluate for that patch. And if you're in at t equals 1.47, then you know you're in this, and you use a different polynomial. Well, different in the sense that it has different coefficients, but its form is the same. And what you can see here is for the kth patch. That is to say, if the patch goes from k to k plus 1, t is in that thing, and the control points are k minus 1, k plus 1, and k plus 2, and you're given control values, p sub k minus 1, p sub k plus 1, and p sub k plus 2, the spline function is given here. There are 4 basis polynomials. They're 1/6 times this, and 1/6 times this, 1/6 times this, and 1/6 times this, respectively. 4 different control polynomials. And the pKs, did I say control? Let me say all over again. These are basis polynomials. This is a basis polynomial. The first one, the second one, the third one, there's 4 basis polynomials. And the coefficients of the basis polynomials are the control values, right? So it's k minus 1 for B-spline. The control values are the 2 surrounding the patch, and 1 to the left and 1 to the right, right? And so if you're over here, then the patch goes from the n minus, you use the n minus third, the n minus second, the n minus 1th, and the nth. for this patch between n minus 2 and n minus 1. And what do you do when if the data is in this end patch or this end patch? And the answer is, well, you're not really intended to want to have values there. But if you must, you can evaluate take the polynomial that you produce for 1, 2, and use it in that end patch. Okay? So, these guys let's see if we can get are written, this is Qi of t. For B-splines are cubic. Okay, there are 4 basis polynomials, each cubic in T. So the result is a weighted sum of cubics, which is a cubic. Right? There exist quadratic splines, there exist quartic splines, there exist lots of different kinds of splines, and there exist different levels of locality. Some of them just take the points surrounding the patch. I mean, immediately adjacent at the 2 ends of the patch. Some take, like this one, those 2 and 2 more outside of it. There are ones that can take even a bigger interval. We call it the aperture, is the range of control values that contribute to the polynomial in a particular patch. Right? So over here, the brace shows the aperture for the patch that goes from 1 to 2. The data comes from the aperture. The place it's applied is in the patch. And there's all sorts of ways in which the patches fit together. They don't have to fit together exactly at the patch boundaries. It's possible for a patch to go from halfway between here to halfway between here, for example. And they fit together at the middle, the so-called knots, K-N-O-T, knots. But here, for B-splines in particular, the patches are the way I've set it up here. The apertures include the 2 points bounding the patch, the 2 control points, and 2 more, one on each side. Clear? Okay. And the way it's expressed here, the coefficients, for example, -1, 3, -3, 1, the first column, are the coefficients of the first basis polynomial. What is it? -1, 3, -3, 1. The cubic coefficient, the quadratic coefficient, the linear coefficient, and the 0th order, the constant. Right? And the second column, 3, 6, -0, 4, 3, -6, 0, 4. And the final column, for example, 1, 0, 0, 0. So it's just a cubic polynomial and a pure cubic in T minus K. And the quadratic, linear, and constant terms are all have zero coefficients. That is to say, they have 0. And so, okay, so the point is, this set of basis polynomials has been worked out by some wonderful other scientists that you could reproduce if you needed to, but you don't need to, because they've worked it out so that these polynomials will fit together just right at the knots. Right? These polynomial patches. And all you need to do is to provide the p's, and then you just use this formula for the K patch to get Qi of t for t in that patch. So far, so good? Okay, so we have these B split. Yeah, question? Yeah, thank you.
So like, are those, like we always use this matrix, or do we have to calculate matrix somehow?
You always use that matrix.
Oh, okay.
Those matrix are the B-spline basis polynomials. If you're using B-splines, those are the basis polynomials. Only time you would change that matrix is if you weren't using B-splines, you're using some other kind of spline. Okay, so the theory of splines is reasonably well-developed piece of numerical computing. And the best reference I know is the book by Elaine Cohen et al. Elaine is a professor at the University of Utah that we've had the good fortune of having here in Chapel Hill for a sabbatical and some collaboration. But never mind, that's her book. There's also some discussion of B-splines in the Birchfield book that you're, I hope, familiar with by now. And it's given here, the reference there. Okay, so far so good. We now have an ability to take a collection of control values, pk, and to apply this approximation for whichever t that we want, which will determine the interval. Notice that the kth patch has k in the polynomial. That's the t minus ti. The ti is I, just the value I in this case where the ith point is considered to be at an integer value. Okay, but now we're interested in images. Okay, so now our control points are going to be in 2D, right? We're going to have a value designating what our polynomial is going to be, and we're going to have a patch that's a little square. So it's going to go from t equals something to something in x, and t equals something to something else in y, yeah? And we're going to apply this thing separably, meaning we're going to take each one of the rows and consider it a one-dimensional x thing, right? And we're going to produce t values in x that have to do with the spacing in y that we're going to want. So we're going to produce, for this patch, if we're trying to produce a final result, that is 256 by 256, and we have patches that are 64 wide, right, then we're going to need 256 divided by 64, right, which is whatever, right, what 2 to the 8th divided by 2 to the 6th is 2 squared. Yeah, we're going to need 4 values per, to evaluate here at 4 spacing values, because we're going to need them for producing the y interpolations. So for each one of these rows, we're going to have 4 values here, and 4 values here, and so on, and 4 values here. Okay? And after we have those values, we're going to just have new direction, namely the y direction, and we're going to use these interpolated values to produce successive values in y. That is to say, the coefficients in y are going to be the results of the interpolation in the rows in x. And if you have z, you're now going to have a plane and a plane and a plane and a plane in z, each one of which is now going to be 256 by 256, for example, but where the spacing of the planes may be 64 by 64, and then you use those coefficients that you've produced in y after having done in x, you're going to use them as coefficients for the z interpolation. It's applied separably, first in one dimension, then in the next dimension. That's what we mean by separably. Right? Yes?
Are those points approximations?
The values of the splines are indeed approximations, always in B-splines. And so you're using approximations in x as coefficients for the approximations in y. Yes? Okay. So, any question? Yes.
So does that mean you do, like, you'd calculate 4 times the number of, like, polynomials in y as you would in x, because you're using 4 approximation values between each of the x to calculate the y.
Yeah, you're going to have to, in this particular example, compute for every column in y that you want, you're going to need to use the spacing in x that you've evaluated to. So we've turned x from something that was 64, spacing 64, into something that's spacing 256, spacing so that there are 256 points, and there are going to be 256 different y-splines to compute.
So then if you did that again for a third dimension, you'd have another factor. Okay.
You bet.
Okay.
Absolutely. So what you end up with in 2D, for example, is cubics in x whose coefficients that become coefficients of cubics in y, which is to say the product of the two is going to be these pKs are going to, when you're applying it in the y direction, are going to be themselves polynomials in x. And so you're going to have a polynomial in x times a polynomial in y, where the t in the x polynomial is according to where you are along the x dimension, and the t is where you, depending on where you are in the y dimension. So if you have a particular value of t that's within this square, within this patch, it'll actually be within some range of t in x and some other range of t in y, right? And those would be the two t's that you use respectively for the x polynomials and the y polynomials, right? Bit of a complication, but it all makes sense. It's just cubic polynomials that become coefficients of other, in cubic polynomials in one dimension that become coefficients of cubic polynomials in the other dimension. Further questions? So why the heck do I have these p's underlined? Because so far my examples is that the p's are just scalar values, right? They are coefficients, scalar coefficients. But some of the applications that we're going to talk about, the p's themselves are going to be tuples. And we'll see that in a moment now. Okay, so we're talking about a bunch of possible reasons to have this nice scale and locality chosen approximations. So, if you take an image, let's say it's 1,000 by 1,000, 1024 by 1024, and you take a spacing of control points that are such that it divides the 1024 through the 10th into 64 subintervals, then you will, if you let the control values be average over a region around them, right? So now this control value is actually averaging all the pixel values around that control point. Okay, so you're going to, this averaging is going to give you a low resolution approximation to the value here. And if you use those average values as the control points, then you will get a heavily smoothed version of the original image. It's the same stuff we've been talking about. If you work it out, you're applying apertures that depend on, that are the particular regions around the patch. So for this patch, the aperture would be this one here. The aperture would be that. So we're getting a heavily smooth version of the image. And if the original image was known to be some desired image plus a bias field, some reason or other there's this extra intensity pattern that is on top of that, and you know it's smooth. So the idea is if that's the case, then the spline approximation can be understood to be what we want to do to estimate the bias field. It's spam. Anyway, so this is the bias field, and if it was understood to be additive, a bias, then we're going to subtract it from the original image at all the pixel values. We evaluate the spline at each pixel value. We subtract this out, and now we have a reasonable approximation of the bias-free image. In that case, these p's are going to be intensity values, simple scalars. Or we may know that our camera has different sensitivity at different positions. So at some particular position where in the image we're highly sensitive. And at some other position we have less sensitivity in our camera. Right? Meaning if the sensitivity here is 10 times the sensitivity there, we're going to get 10 times some base intensity from the scene here, and only 1 times the base intensity here. Right? Okay, so it's multiplicative, in which case we're going to play this spline game, but we're going to take the resulting smoothed image and subtract it, and divide it by the base image to remove this variation in sensitivity. So if it was additive, it's a bias, you subtract it. If it was multiplicative, you divide by this thing. Okay, in both cases, however, the pKs are just intensity values. Okay? But now I'm going to talk about a new application that's pretty important. And to do that, I need some more board space. So if I can find the eraser, I'll make myself some more board space. Another one of the weaknesses of whiteboards is that they not only don't necessarily pick up a pen and write, but when you erase, you don't necessarily erase fully. Okay, so now let's consider the problem of distorted images. So far, we have not been talking about distortion. We've been talking about cameras that blur, but not ones that take a position in the image and actually have it appear at a different position, right? So they take the pixels in one region and scrunch them together, in another region they pull them apart. They distort the image. You can't believe the position very well. This is a nonlinear operation in general. And therefore, since we were talking about linear shift invariant operators till now, not within the bailiwick of the methods we've talked about so far. But this happens all the time. In astronomical images, the light from some star not only is blurred by passing through some gas, but there's some diffraction or what have you in the atmosphere that causes, at some places, depending on what gas is there in outer space, to cause distortion. MR, magnetic resonance imaging, has built into it, the way it's made, that it does indeed produce distortion. One use special coils, for example, if you're imaging the brain, that go up here, and they not only vary the sensitivity, make it highly sensitive to the places in the brain that are near that coil, but they also produce distortions as a result of the position of the coil. Images have distortion, and we haven't talked about that so far. And so what we want to be able to do for image processing is undistort the image. Right? We want to correct for the distortion. Or alternatively, Emma back there has data on cells. And she has, let's say, 10,000 cells. Okay? And each one is slightly conformed differently than the other cell. Right? So one is a little bit stretched this way, another one is stretched that way, compressed this way, compressed. And she wants to get statistics on cells, which means she needs to distort each one of the cells into a common cell or layout that will then allow her to say that a particular pixel in the distorted cell 1 and the same pixel in the distorted cell 2 are in correspondence. In which case she needs to distort one cell image into the common framework and the second one by a different amount. This is called deformable registration. Okay? And so we have this general idea of wanting to produce deformable registration, and which is to say we want to be able to apply a deformation function so we want to have a deformation function that takes a particular value of x, I'll just call it def, and produces a place that x moves to, x prime. Right, so now we have a bunch of places, well, and all the pixels in the image. And for every one of them, we want to say this x moves to that x prime, and this x moves to that x prime, and so on, right? We're trying to shift pixels from x coordinates to x prime coordinates, old location to new location. We're trying to deform the image. And so some places the deformations will push the pixel values apart, and some will pull them together. Sometimes it'll push the pixels that way, sometimes it'll move them that way. And we need to compute this function Okay, how do we do that? Well, one reasonable way to do it, due to Daniel Ruckert, at the time he invented this method that he called free-form deformation. He was at Imperial College in London, but today he is in Munich, Germany, a professor there. And the idea is we're going to have control points just like before. But now the control values are going to be vectors. It just says at the control point, the control value says where that control point moves to. Or at least where it approximately moves to, because the the B-splines produces an approximation, not an interpolation. Right? That's fine. So all it changes is the values at the control points are no longer scalars, they're vectors. Which all that changes is that. So now every control value has a delta x and a delta y and a delta z component, if you're in 3D. Or in 2D, delta x and a delta y. Other than that, spline's the same. What you're strictly doing is having a spline for the delta x components of the deformation vectors, a different spline, that is to say different coefficients for the delta y components, since now a particular piece of K is going to be a delta x, a delta y, and a delta z. And so you're going to have coefficients for the x one and different coefficients for the y and different scalar coefficients for z. Okay? Still applied separately. And now, according to Rickert's method, what you want to do is to optimize the choice of these control, should have an underline on it. These control vectors, these control deformation vectors, so as to optimize some match between the information in one of the images and another image. So if you're trying to register two images, what you want is to make, after you apply the deformations on the first image, you would like to optimally match the corresponding intensities in the target image. So you're given two images, you're going to deform image one into image two, and you're going to pick these PKs that in turn turn into splines so that at all the pixel values you get as much match as you can between the deformed version of the moving image and the target image. Okay? So the main point here is really two parts. First of all, you've learned something about how to build a deformation. Secondly, you've seen that splines can have coefficients that are not necessarily scalars, but are themselves vectors. Who? Questions? I'm done with splines. It's complex, but it's not conceptually hard if you keep your concerns straight. Yes.
When we apply the spline separately, does it matter which direction we do first?
In which order you do X and Y and Z? Very good question. The answer is no. Yeah, it turns out that if you did it first in Y and then in X, you'd get the same result as if you did first in X and then in Y. But by the way, it does matter what X and Y are. If you try to apply it with a pattern that were diagonally applied first and then the opposite diagonal, then you wouldn't get the same value as if you applied an X and Y or Y and X. Yeah.
When you applied an X and Y, where did the X and Y terms come into play in the formula?
Well, when you apply an X, these T's are spacing in the X direction. When you apply it in Y, these T's are positions along the Y direction. Right? So I mean, if you're trying to evaluate this thing at t equals t sub x, I'll say. T sub x equals 7.8 and t sub y equals 14.3. Then I'm going to be in a patch that is between 7 and 8 in x, and a patch that's within between 14 and 15 in y, right? And I'm going to have that patch with the x, where t is 7.8 and k equals 7, for x, to provide the x coefficients. And then I'm going to use those coefficients for t point y equals 14.3 and k equals 14. And y. Does that answer the question? Good. Okay. We'll come back a little bit for deformable registration, or different deformable deformation transformations, when we do geometric transformations, which will be a couple of topics after this one, okay? But for now, this is all I'm going to say about its splines' possible use for producing deformations. I can say one further thing right now, and that is I can play multi-scale games now. So I can start off with maybe 16 by 16 control points and get some spline that I can subtract off from the image. Okay, so I have Q, sorry, this should have been K. Someone should have yelled long since that I wrote down I there. It's I on the screen, but I'm used K as the subscript here. But I'm going to now consider so 16 by 16 control points with their apertures, and I'm going to have a Q sub I at any Tx, Ty, and I'm going to subtract that off from image at that Tx, Ty. And so now I have described the image at a scale proportional to the apertures associated with the 16 by 16 control points, which are what? 3 times the spacing, 3 times the size of the patches, these things. Okay, so now I have applied an aperture associated with that scale. And now what I have left, ideally, is information at smaller scale. So I take these guys, and I now use them for, let's say, 32 by 32 control points. So I will now try to represent not the original image, but the image after you've taken a residue against its approximation with large apertures. In other words, large scale information. And that's going to produce a new spline, R sub I of TXTY, where the spacings are going to, instead of being the original spacing, it's going to be smaller spacing. So you're going to have smaller apertures. Smaller patches, correspondingly smaller apertures. Right? So instead of 16 by 16, I'm going to take the results here and evaluate them the half spacing using the spline and subtract out these from the original image, and then I'm going to use those as control points for a smaller scale spline. And I'm going to subtract that out from this minus this, and get the residue that I can then use maybe a 64 by 64 control point spline, and so on. So we have this general idea of residue that can be applied to splines. We take the whole image, we figure out how to approximate it at large scale, we subtract out the large scale approximation, and we get the residue, which is presumably smaller scale, which we then use a spline that is appropriate for that smaller scale. That is to say, with smaller patches and correspondingly smaller apertures. Okay, so we're now thinking of having images that are going to have basis images that are going to have locality, u sub 0. That's the center of a region. In this case, the center of this example, the center of the spline patch. They're going to have a level of detail. In our case, the level of detail is related to the size of the patch, and they're going to have a aperture size, which for splines is 3 times the width of the size of the patch. And this idea that the sigma and the level of detail are going to be in proportion to each other is going to be something that we're going to like, okay? But it's not conceptually necessary. It's desirable from a thinking point of view, if you will. And so we have these basis images, psi, at various levels of detail, and they are centered at u sub 0. They have to do with a position, a locality indicated by u sub 0, and they are evaluated at various values of u in that locality, and they have an aperture sigma. And you have coefficients, just like before, but now the basis images are all over. You have a set of basis images for the first upper left-hand corner, another set of basis images for that, another set of basis images for that. That is to say, in the original image, you're going to have maybe initially levels of locality that you're going to have a set of basis images for this patch, and for that patch, and for that patch, and for that patch, and you're going to use it for everywhere in the patch. Right? You're going to get coefficients for those basis images. And then we're going to subtract out that representation And I've got a new set of basis images for all these little smaller patches. Well, this is just what we've been doing with the splines, right? That's a particular way of producing these basis images. They're just these basis polynomials that we've been using for the splines. And so on. So we're going to have basis images that are different for locality and also to have associated levels of detail and scale. And aperture size, I should say. Level of detail and aperture size. Now, we've been talking about splines as an example, but now let's come back to these other ways of producing multi-scale approximations that we're talking about. So imagine that besides splines, we've been talking about Gaussian derivative representations. We've been talking about the Gabor wavelet representations, which are sinusoids under a Gaussian. And we're going to be talking about the so-called orthogonal wavelets. Okay, so we're really talking about 4 examples of this idea of basis images with locality and with level of detail and with aperture size. And so if we have something that's based on a Gaussian, as with both the Gaussian derivatives and the sinusoids under a Gaussian, then our aperture size is going to be sigma, and for the Gaussian derivative, the level of detail is the order of the derivative. So first order, 0th order derivative gives you something with no zero crossings across the aperture. The next one, first derivative, has sort of one halfway in between. It halves the size of the lobes. The second derivative is third of the original size. The fourth derivative is about a fourth of them. And you can see here on the screen, this is from Romany's book, what a 20th derivative looks like. It's just it looks pretty sinusoidal under a Gaussian. But it's a Gaussian derivative, and we can understand it to have a wavelength or a level of detail that's the distance here between the corresponding maxima of this 20th derivative of a Gaussian. So this is not quite right. In fact, I'll just fix it on the spot. Good. All right. Okay, sorry for, no, it- gonna have to play some games to make it fit on the screen, but fine, I'll do that after class. The point is that if you have a sinusoid under the Gaussian, then the level of detail is the wavelength of that corresponding sinusoidal coefficient after multiplying by the Gaussian, the locally centered Gaussian. For derivative, it's the order, is the level of detail. Roughly the same idea. As I told you in the last lecture, you don't get significantly different results whether you use Gaussian derivatives or whether you use sinusoids under the Gaussian, the Gabor results. And we'll see that for the orthogonal wavelet, there's going to be a similar sort of arrangement where we're going to have orthogonal wavelets that are global across the whole image, that have the full image as its aperture, that have half the image divided it into halves in each dimension as the basis, have the image divided into quarters in each dimension, that is to say quarter by a quarter, and so on. And we're going to play the same residue game. And the notion is the same. We're going to have this subdivision by both aperture size and position. And we're going to have, if you will, coefficients of them that we can compute by the means appropriate for that particular type of basis image. And we're going to pile these all up, summing over all the different levels of aperture size sigma and each aperture size is going to have an associated collection of levels of detail. So it might be, a small number of derivative orders in the case of derivatives of Gaussian, or a small number of frequencies that are relevant. And this begs the question, how should the levels of detail and the sigmas be related to each other? And that's going to bring us to this idea that we've been already talking about, of having large-scale ones and then residues that get evaluated into smaller scale ones, and then residues from that give you yet smaller scale ones, where the level of detail is going to be in proportion to, the level of details in use are going to be in proportion to the aperture sizes. What a perfect stopping time. I don't know how I did it. Questions before we stop? Okay. See you next time.